Sound waves are a type of mechanical wave that are longitudinal. That is, the oscillations of the elements move through the medium in the same direction that the wave travels. So if we look at the speed of sound in a medium, we find that the speed of sound is similar to a transverse wave, tau over mu, which is proportional to elasticity over inertia. But for a sound wave in a liquid, elasticity is associated with compression and expansion of the medium. And this involves a change in volume with pressure. And that's given by the bulk modulus, B, if you remember. And that's equal to minus the change in pressure over the change in volume over the starting volume. And the units for these, for B, is pascals, PA. So basically, the change in pressure is proportional to 1 over the change in volume. The other fact is that the mu in this equation becomes rho, or the density of the medium. So our equation for velocity in the medium then, and this is in a liquid medium, becomes the square root of B over density, where B is the bulk modulus and rho is the density of the medium. And if we're looking at the velocity of sound in a solid, such as a solid rod, V would be the square root of y over rho, where y is equal to Young's modulus. And if we're looking for the velocity of sound in a gas, that becomes the square root of gamma RT over m, where gamma is the ratio of heat capacities, R is the gas constant, and m is the molar mass. And since these are basically constants, you get the velocity of sound in a gas is proportional to the square root of t. But we won't be using these in this video. I just wanted to put that in for completeness. Let's look at a traveling sound wave. And we'll consider that the sound is traveling in a pipe and being produced by a piston. So if we have our pipe, and here's our piston, and the piston moves back and forth, basically in a sinusoidal pattern. So this is similar to simple harmonic motion. We get sound waves where you get areas of compression and areas of expansion. So that would be compression of the medium. That would be expansion of the medium. And between two similar points, that would be a wavelength. And the sound wave is moving in the tube in that direction. So this is a longitudinal wave. The elements of the medium are moving in the direction of the wave itself. So with transverse waves, we used y of x and t to describe the wave, but our sound waves are moving in the x direction. So you might want to use x of x and t, but that becomes confusing. So instead of x, we use s of x and t. So s is for sound waves, and we get our sound wave equation. X of s and t is equal to the amplitude, the maximum displacement, times the cosine of kx minus omega t. So this is the displacement in the x direction. That is your amplitude, which is your maximum displacement. And again, you could use sine here, but we're going to use cosine in this video. And as with transverse waves, we have our definition of terms. K is 2 pi over lambda. Omega is equal to 2 pi over t, which is equal to 2 pi f. Frequency is equal to 1 over t, which is equal to omega over 2 pi. V is equal to omega over k, which is equal to wavelength over t, which is equal to wavelength times frequency. And again, we will use different variations of these to solve problems. Now, sound waves can also be described in terms of pressure variations. So we can write a wave equation for a sound wave in terms of pressure. So change in pressure of x of t is equal to Pm times the sine of kx minus omega t. Because as we've seen in this pipe, the pressure varies along the direction of the wave movement, and you can describe the wave in terms of those pressure differences. So in this equation, this is your change in pressure with respect to position and time, and this Pm is called your pressure amplitude, and that's your maximum pressure of the sound wave. And if you go through the derivations in the textbook, you'll find that Pm is equal to velocity times density of the medium times angular frequency times maximum displacement, which also becomes equal to bulk modulus times omega times S of m. Now let's look at the interference of sound waves. So basically, if we have two sound waves with the same amplitude and wavelength, both going in the plus x direction, with a phase difference of phi, that gives a resulting sound wave s prime of x of t equal to 2 sm cosine 1/2 phi times cosine of kx minus omega t plus 1/2 phi to account for the phase difference. And this basically becomes S prime sub m, the maximum amplitude of the resulting wave. Now, what if we have two waves with the same amplitude and wavelength that are in phase but travel paths of different lengths to reach a point P? So let's look at this. Let's start with our source 1 and our source 2. But in this case, they're traveling the same length to point P. So this is L1 and this is L2. And they're both in phase, so phi equals 0. That means that at point P, you get constructive interference. Okay, but now we're going to change the lengths that they travel. So here's source 1 and here's source 2. And in this case, point P is over here. So this is length 1 and length 2. So you can see they travel a different distance. This means that at point P, the waves will be out of phase by a difference of phi, and this difference phi will depend upon the lengths of paths 1 and 2. So basically we find that phi is equal to the difference in lengths divided by wavelength times 2 pi. This is what we would find our phase difference to be. Now, if phi is equal to 0 or 2 pi or 4 pi, in other words, an integer number of wavelengths, then that leads to fully constructive interference, because basically the waves are not out of phase. So basically, if phi is equal to n times 2 pi, where n is equal to 0, 1, 2, etc. Okay, this gives delta L over lambda will give a whole wavelength phase shift, and you get constructive interference. Now, if phi would turn out to be pi, 3 pi, 5 pi, etc., okay, then they are half a wavelength out of phase, and you get fully destructive interference. So in this case, phi would have to be equal to 2n plus 1 times pi, where n is equal to 0, 1, 2, etc. Or delta L over lambda becomes 1/2, 3/2, 5/2. In other words, you get a half wavelength phase shift causing fully destructive interference. This is how noise reduction earphones work. When the earphones hear a sound coming in, it shifts the phase by half a wavelength, which then cancels out the sound coming in. Let's talk about the intensity of the sound. we're not talking about loudness, which is what the listener perceives. Intensity is actually defined as the rate of energy transferred to a surface per unit time, or in other words, the power in the wave over the surface area that the wave hits. And if you go through your derivations, you'll see that that's equal to 1/2 rho v omega squared sm squared, which also becomes equal to 1/2 the square root of rho times the bulk modulus times omega squared times sm squared. So rho is equal to the density of the medium, v is the velocity of the wave. Now sound spreads out spherically. So if we have a source, we would see the sound spreading out if it's not in some kind of tube in all directions spherically, and this would be r, the radius. So in this case, intensity is equal to power over area, and the area of a sphere is 4 pi r squared. Sometimes it's more convenient to express intensity in terms of the pressure amplitude. So if we go through the derivation of that, we will get I equals pressure amplitude squared over 2 rho v, which also equals pressure amplitude squared over 2 times the square root of rho and the bulk modulus. Now let's look at the decibel scale. Since we can have an intensity of sound that varies over a range of 10 to the 12th, we find that if we use a logarithmic scale, we're able to better describe intensity. And this is the sound level. And the sound level, beta, is equal to 10 times the log of I over IO. And the units are decibels. And I0 is equal to a reference value. It's a reference level that is equal to 10 to the minus 12 watts per meter squared. And that is actually the very lowest limit of human hearing. And that's why we use that as I sub 0. And if you notice that when the intensity of our sound is equal to I sub 0, beta becomes 10 times the log of 1, which is equal to 0 decibels. So when we have a sound equal to our reference level, we're saying that that sound is so low we can't hear it. Let's look at sounds we hear from musical instruments. We can set up standing waves with sound. Sound waves can reflect back at the end of a pipe, whether that pipe end is open or closed. At certain resonant frequencies, we will get a standing wave in that pipe. We will also find that we get displacement nodes and antinodes that are areas of zero displacement for nodes and maximum displacement for antinodes. And we also get pressure nodes and antinodes. And they are areas of zero pressure for pressure nodes and maximum pressure for pressure antinodes. Displacement nodes and pressure nodes are opposite. A pressure node always occurs at a displacement antinode, and a pressure antinode always occurs at a displacement node. So now I'd like to look at standing waves that form in musical instruments. And on the left, you see a pipe with two open ends, and on the right, you see a pipe with one closed end. So if we go to the left, you can see how the standing waves can form. The harmonic number n equals 1, which is the fundamental frequency or first harmonic. You can see that in this pipe of length L, there is half a wavelength. So L is equal to half a wavelength, so a full wavelength is equal to 2L. And you have your node where there's 0 amplitude, and your antinodes at the ends where the pipes are open. And you can also then see where n equals 2, you have your second harmonic, and n equals 3. So you can go through n equals 1, 2, 3, 4, and basically any harmonic can form. However, when you have a closed end on a pipe, that restricts which harmonics can form due to the standing waves that can form. In this case, there has to be a node at the closed end of the pipe and an antinode at the open end. So the first harmonic would give you 1/4 of a wavelength. That's why a full wavelength is equal to 4 times L, the length of the pipe. You could see that you can't get standing waves where n is an even number, like n equals 2 or n equals 4. So basically, with a closed-ended pipe, you can only get odd numbers of harmonics. So for a pipe where both ends are open, the wavelength is equal to 2L over n, where n equals 1, 2, 3, etc. And our resonant frequency, F sub n, is equal to V over L over lambda, which is NV over 2L, where again n is 1, 2, 3. So this gives the equation for finding the different resonant frequencies of a pipe with both open ends of length L. Similarly, the wavelength with one closed end is equal to 4L over n, where n in this case is 1, 3, 5, etc. And the resonant frequency would be V over lambda, which turns out to be NV over 4L, where n is equal to 1, 3, or 5, etc. So these are the resonant frequencies for a pipe with one closed end. Now let's talk about beats and beat frequency. Beats occur when you have two sound waves with equal amplitude but slightly different frequencies. We actually end up hearing the average frequency of the two waves, plus a large variation in the intensity. And it's these intensity variations that are the beats. So here you can see an example of two waves of slightly different frequency that are combined to give you this resultant wave. And you can see the variation in the intensity. And these are what we hear as the beats. And we can write an equation for this resulting wave, and that is S of t is equal to 2 S sub m cosine omega prime t times cosine omega t, where omega prime is equal to 1/2 omega 1 minus omega 2, and omega is equal to 1/2 omega 1 plus omega 2. And that refers to the two different waves that cause the beat. We can also determine our beat frequency, the frequency of how often we hear the beats, and that's just equal to frequency 1 minus frequency 2. And we use beat frequency to tune instruments. You can actually hear the beats between two instruments that are slightly out of tune, and as you tune them to equal frequencies, the beats go away. Now we can discuss the Doppler effect. And everybody's heard this. A train blowing its whistle that approaches you and then moves further away, you hear a shift in the frequency. Same thing with a siren on a police car. And basically, the Doppler effect, or the Doppler shift, is a change in the frequency of a sound when approaching it or moving away from it. As you approach the sound, or the sound approaches you, the frequency increases, and as the sound gets further away, the frequency decreases. And you can write an equation for the new frequency. This is the frequency that we detect, and that's equal to the frequency of the source of the sound times velocity of sound plus or minus the velocity that the detector is moving, which that could be your ear, over velocity of sound plus or minus the velocity of the source. So v is equal to the speed of sound. V sub d is equal to the detector's speed relative to air, and v of s is equal to the source speed relative to air. Now, this equation is a little bit complicated, but there are rules that determine how you use it. So here are the rules. When the detector or source is getting closer, then the plus or minus sign must give an increase in frequency. And the other rule is when the detector or source is getting farther away or moving apart, then the plus or minus sign must be used to give a decrease in the frequency. And we can give some examples of this. So examples of this are, if the detector is moving towards the source, then you use the plus sign in the numerator. If the detector is moving away from the source, then you use the negative sign in the numerator. And if the detector is stationary, then the velocity of the detector becomes 0. Also, if the source is moving towards the detector, and again that could be your ear, then you use the negative sign in the denominator. And if the source is moving away from the detector, you use the positive sign in the denominator. And if the source is stationary, then the velocity of the source is equal to 0. So it sounds complicated, but you just have to follow these rules, especially these examples, to be able to know which plus or minus signs to use in the numerator and denominator. And light can also have a Doppler shift. We won't get into it now, but basically for light, the frequency received is equal to the frequency of the source times the square root of c minus v over c plus v, where c is the speed of light and v is the speed of sound. So police use this with radar to catch speeders. It looks at the Doppler shift of the electromagnetic wave that's bouncing back from the car. So that's how radar works. Now let's look at supersonic speed, and we'll get into shock waves too. So if a source is moving towards a stationary detector, again, your ear, at the speed of sound, then the velocity of the source, and let's say that's a jet, is equal to the velocity of sound. Then you get f prime is equal to frequency of the source times v plus or minus v sub d over v of the sound minus v of the source. And again, v of the source and v of the sound are equal in this example, so you get that over 0, which becomes infinity. And what happens then is the source or the jet is moving along its own wavefront. But what if v of the source is greater than velocity of sound? This is called supersonic speed. Well, what happens then is you get a bunching up of wave fronts at the front of the source or the jet. And that causes a rapid increase and decrease in pressure, which is what we perceive as a shock wave. So in this case, if we have our source or jet moving that way, we get wave fronts that look like this, building up. And if we look at that wave front, we have an angle here, theta, and theta is called the Mach cone angle. This is the Mach cone, which is the wave fronts, and we have that angle. And we can find theta because the sine of theta is equal to the velocity of sound over the velocity of the source or the jet. We also have what's called a Mach number, and that's equal to the velocity of our source over the velocity of sound. So this becomes 1 over the Mach number. So when a jet is going Mach 2, that means it's going 2 times the speed of sound. Now, shock waves are used in medicine to break up kidney stones and gallstones. That's called extracorporeal shockwave lithotripsy. Let's do some problems. The first one reads, a sound wave can be described in terms of pressure changes. One sound wave is given by the equation P equals 2.4 sine pi x minus 330 pi t. What is the pressure, amplitude, frequency, wavelength, and speed of this wave? So our pressure wave equation is given as Pm times the sine of kx minus omega t. So if we compare these two equations, we see Pm is equal to 2.4, k is equal to pi, and omega is equal to 330 times pi. So to answer this problem, our pressure amplitude is equal to 2.4 newtons per meter squared. Our frequency is omega over 2 pi, which is equal to 330 pi over 2 pi, which is equal to 165 hertz. The wavelength is equal to 2 pi over k, which is equal to 2 pi over pi, which is equal to 2 meters. And the velocity of the wave is equal to lambda times f, which is equal to 165 times 2, which is equal to 330 meters per second. Here's another problem. The ear can tolerate sound pressures up to about 30 newtons per meter squared. What would be the maximum displacement for a sound wave with this pressure having a frequency of 2000 hertz? Assume the density of air is 1.2 kilograms per meter squared and the speed of sound is 330 meters per second. Well, one of our equations gives the pressure amplitude equal to velocity times density times omega times the displacement amplitude. So if we solve for the displacement amplitude, which is the maximum displacement, it's x is equal to Pm over V rho omega, and we can plug these in. That's 30 over velocity, which is 330, times density, 1.2. Now, omega is equal to 2 pi times the frequency. So, to get omega here, that would be 2 pi times the frequency, which is 2000. So if you go through this calculation, you end up with the maximum displacement is equal to 6 times 10 to the minus 6 meters. Here's another problem. Two horns are sounded with frequencies of 550 and 554 hertz. A person is between them and is walking towards the lower frequency horn at 1.5 meters per second. What is the beat frequency that the person hears? Assume the velocity of sound is 330 meters per second. So let's make a little diagram. Here's our first horn, source 1 at 550 hertz. And here's source 2 at 554 hertz. And the person is walking between them with a velocity of 1.5 meters per second. So the velocity of our person or detector is 1.5 meters per second. The velocity of sound is 330 meters per second. And the velocity of our sources are 0. So let's set this up. We need to get the frequencies that the person hears from both sources, because there is a Doppler effect that will occur. So if we say from source 1, the frequency that he hears through the Doppler effect is equal to the initial frequency of source 1 times V plus V of the detector over V plus V of the source is 0. And we use the plus sign up here because that gives us an increased frequency, which you get when you go closer to a source. And also because if you go back and look at the rules, it says that if the detector moves towards the source, you use a plus sign in the numerator. So this becomes f of 1 times v of sound times v of the detector over v. And this was for the source 1. Now let's look at the Doppler frequency that would be detected from source 2. So that's equal to the frequency of source 2 times v of sound minus v of the detector over v of sound plus 0. And we're using a minus sign in the numerator because we're walking away from the source 2, and because that is what the rules tell us to do. So that's equal to f2 times v minus v detector over v of sound. So we have our beat frequency is equal to f1 prime minus f2 prime, which is what the person hears. So we can put that in. That's equal to f1 times v plus vd over v minus f2 times v minus vd over v. And this becomes v of the detector times velocity of sound times f1 plus f2 plus f1 minus f2 if you work out the algebra. And if we put in the values, we get 1.5 over 330 times 550 plus 554 plus 550 minus 554. And if you go through that calculation, you end up with 1 hertz. So the beat that the person hears as he walks between these two sources is 1 beat per second. Continuing with the problems. A band has a sound level of 100 decibels at a distance of 15 meters. The band is playing into a hemispheric auditorium. What is the power output of the band? Okay, so this gets into the decibel scale. We know that the sound level is equal to 10 times the log of intensity over IO, which is the reference intensity. So we're given that the sound level is 100 decibels, so that's equal to 10 times the log of I over IO, which the reference is 10 to the minus 12th. So we divide 10 into 100, we get 10 is equal to the log of I over 10 to the minus 12th, which is equal to the log of I minus the log of 10 to the minus 12th. So if we solve for the log of I, because we're looking for I, log of I is equal to 10 plus the log of 10 to the minus 12th, which is equal to 10 minus 12, or the log of I is equal to a minus 2. And if you calculate what I is, that's equal to 0.01. Now we're looking for the power of the band, which we know is equal to I times A. So we know that the band is playing into a hemispheric auditorium. So the area of a sphere is equal to 4 pi r squared. But a hemisphere is half of that area, so that's equal to 2 pi r squared. So if we go back to our power is equal to 0.01 times 2 pi r squared is 15 squared, and that's equal to 14.1 watts. Here's another problem. A sound source has an intensity of 5 times 10 to the minus 3 watts per meter squared at 10 meters. What would the intensity be at 4 meters? Well, first we're going to assume that the sound is radiating spherically, and as sound radiates, the power stays the same. So our power at 10 meters is going to equal our power at 4 meters. So our power at 10 meters would be intensity at 10 meters times the area at 10 meters. That's equal to the intensity at 4 meters times the area at 4 meters. And the area of a sphere is equal to 4 pi r squared. So this becomes intensity at 10 meters times 4 pi, or r is 10 squared, is equal to intensity at 4 meters times 4 pi times 4 squared. And these cancel out. I at 10 is 5 times 10 to minus 3 watts per meter squared times 100 is equal to the intensity at 4 times 16. this becomes 0.5 is equal to I at 4 times 16, or intensity at 4 meters is equal to 0.5 over 16, which is equal to 0.031. So our intensity at 4 meters would be equal to 3 times 10 to the minus 2 watts per meter squared. Next, what is the loss in decibels if you double your distance from a sound source? Assume constant power output. So if we have a source of sound and we go from a distance R1, we double it to R2, where R2 equals 2 times R1. What happens to our decibel level? Well, we know that the power stays the same as it travels, so power at point 1 is equal to power at point 2. So intensity times area at point 1 equals intensity times area at point 2. So intensity times 4 pi R1 squared is equal to intensity, that's 1 of 2, times 4 pi R2 squared. But R2 is equal to 2 times R1, so that's equal to I2 times 16 times pi R1 squared. So from this we get I1 is equal to 4 times I2. And we want to know what happens to the decibel level, the sound level. So we know the sound level of at the first radius is equal to 10 times the log of I1 over I0. And we know the sound level, beta 2, at R2 is equal to 10 times the log of I2 over I0. So we want to know what our decibel loss is. So the decibel loss is basically a change in our decibel level, which is beta 1 minus beta 2. And that's equal to 10 log I1 over I0 minus 10 log I2 over I0. And if we expand out the logarithms, we get 10 times log of I1 minus log of I0 minus log of I2 plus the log of I0. And these two cancel out. We end up with a 10 times the log of I1 minus the log of I2, which is equal to 10 times the log of I1 over I2. But that's equal to 10 times the log of, well, I1 is 4 times I2. So 4 times I2 over I2, which then becomes 10 times the log of 4, which is equal to 10 times 0.6, or it's equal to 6 decibels. So a decibel loss by doubling the distance is equal to 6 decibels. Our next problem is a man walks away from a building towards a friend at 1 meter per second. While walking, he blows an air horn. His friend hears beats at 6 beats per second. What is the frequency of the air horn? Assume the speed of sound is 340 meters per second. So what we're talking about here is you have a building, a man walking away from the building, and a friend. So he has this horn that he's blowing, and he has the direct sound coming to the friend from the horn, plus he has the sound bouncing off the building, an echo or reverberation. So there's actually two sound waves coming towards him. We'll call that frequency of the direct wave and the frequency of the reflected wave. So we're given the beat frequency, which is the difference in these waves, and the Doppler shifts depend upon the original frequency of the horn, and we'll call that. Now, in both cases, the friend, who's the detector, is not moving, so the velocity of the detector is equal to 0. And we have velocity of sound is equal to 340 meters per second. And the velocity of sound can vary depending upon air temperature and other factors. So let's start with the frequency of the direct wave. And again, these undergo Doppler shifts. So the frequency of the direct wave that the friend hears is equal to the frequency of the source times velocity of sound plus 0, because the detector isn't moving, over the velocity of sound minus the velocity of the man walking towards him. And we should mention the velocity of the man walking towards his friend is 1 meter per second. So this is the frequency, the Doppler shift of the direct horn sound, and that's equal to f of s times velocity of sound over velocity of sound minus velocity of man. Now let's look at the frequency of the reflected sound that the man hears. So in this case, it's f of s times v plus 0, because the detector, the man, is not moving, over velocity plus v of m. Now in the first case, we use a minus sign because we want to get a higher frequency because he's walking towards the detector. In the second instance, the sound is bouncing off the wall, off the building. So as the man is walking this way, it's actually taking a longer path to get to him. So we would expect the frequency to decrease. So that's why we use positive sign and denominator here. So this becomes Fs times V over V plus Vm. Now, our beat frequency is F of the detected frequency minus the frequency of reflected. So if we put these in, we get Fs of V over V minus Vm minus F of the source times V over V plus Vm, which equals Fs times velocity of sound times 1 over V minus Vm minus 1 over V plus Vm, which, if you go through the algebraic maneuvers, you get F of S times V times 2 times the velocity of the man over V minus Vm times V plus Vm. And again, this is the beat frequency. And we're looking for the original frequency of the horn, the source, which is Fs. So if we solve for Fs, that's equal to the beat frequency divided by 2 times velocity of the man times V minus Vm times V plus Vm, which is equal to, the beat frequency in this case is 6 over 2 times the velocity of sound is 340 times the velocity of the man times 340 minus 1 times 340 plus 1, which equals 6 over 680 times 339 times 341, or the frequency of the source is equal to 1020 hertz. Let's do one more problem. A pipe organ is playing through an open pipe. This pipe is suddenly closed, resulting in a second overtone that is 120 hertz higher than the first overtone of the open pipe. What is the fundamental frequency of the open pipe? Well, let's first describe and define a few things. When you have a open pipe versus a closed pipe, the harmonic number in the open pipe could be any number, whereas in a closed pipe it has to be an odd number. So the fundamental frequency of an open pipe would have n equals 1, and the first overtone would be n equals 2. The second overtone would be n equals 3. Whereas in a closed pipe, the fundamental frequency is n equals 1, but the first overtone is n equals 3, and the second overtone is n equals 5, because you can't have even numbers n. I also want to mention that the fundamental frequency is the first harmonic, which is equal to no overtone. The next frequency is the second harmonic, but that's the first overtone. And the third harmonic is equal to the second overtone, and so on. So it gets confusing. This is n equals 1, this is n equals 2, this is n equals 3 for an open pipe. So this gets very confusing unless you're a musician. So let's get back to our problem. So for the open pipe, we know that the frequencies f sub n are given by nv over 2L. So the fundamental frequency, n equals 1, gives the fundamental frequency to be v over 2L. And the first overtone, where n equals 2, gives the frequency to be v over L. Now, in a closed pipe, we're not allowed to have even numbers of n. So our frequencies are given by n times v over 4L. So the second overtone is actually where n equals 5, is given by 5v over 4L. Okay, So this is the first overtone, and this is the second overtone. N is equal to 5. Now, the problem states that the second overtone of the closed pipe, which is F5, minus the first overtone of the open pipe is equal to 120 hertz. And we found these values up here. That's equal to 5V over 4L minus V over L, which gives us V over 4L. So we're trying to find out the fundamental frequency of the open pipe. And if you recall, the fundamental frequency, as shown above, is equal to V over 2L. So we have 120 hertz is equal to V over 4L. Since the fundamental frequency is V over 2L, then we have to multiply the first overtone by 2 to get the fundamental frequency. So a fundamental frequency comes out to be 240 hertz.